Understanding unexpectedly low demand load calculations requires careful consideration of several factors. Let's explore potential explanations and recommended actions when faced with such discrepancies. Firstly, the load study methodology itself needs scrutiny. The consulting firm might not have accounted for all potential loads within the manufacturing facility or office building. Perhaps they employed overly conservative assumptions that significantly underestimate the actual demand. It's crucial to review the methodology in detail, examining what loads were included, the diversity factors applied, and the data collection methods used. Secondly, the time of day during which the load study was conducted can heavily influence the results. If the study was performed during off-peak hours, such as weekends or holidays, the observed demand would naturally be lower than during a typical workday, when all equipment is operational. Consider the manufacturing facility. Its energy consumption likely varies considerably depending on the production schedule. For the office building, lighting, HVAC, and computer usage will be lower outside of regular business hours. Thirdly, the power factor plays a significant role in determining the apparent load current. A low power factor indicates that a substantial portion of the current is reactive, not contributing to actual power consumption. If the load study assumed a low power factor, the calculated demand load would be lower than if a higher power factor was assumed. Power factor correction can significantly improve the efficiency of the electrical system and reduce the required transformer capacity. Fourthly, load diversity can explain a lower than expected demand load. Diversity refers to the fact that not all loads operate simultaneously at their maximum capacity. For instance, a large motor load might only be used intermittently, and its impact on the overall demand load would be less than if it ran continuously. Similarly, in the office building, various pieces of equipment may have staggered usage patterns, preventing them from all drawing maximum power at the same time. In addition to these factors related to the load study itself, other considerations are vital when planning for the new transformer installation. 1. It is advisable to anticipate potential future load increases when selecting the new transformer size. The manufacturing facility may expand its operations, acquire new equipment, or increase its production capacity. The office building may add more workstations, install new servers, or upgrade its HVAC system. Planning for future growth ensures that the transformer has adequate capacity to handle increased demand without becoming overloaded. 2. Having two transformers provides redundancy in case one fails. While you're planning to transition from 6 transformers to a single pad-mounted transformer, it's important to remember the reliability benefit of having multiple units. In the event of a transformer failure, the remaining transformer can continue to supply power to at least a portion of the load, minimizing downtime. If the single new transformer fails, there would be a complete loss of power to both buildings. 3. Underground service drops can introduce voltage drop, which should be taken into account when sizing the transformer. The longer the underground cable run, the greater the voltage drop will be. Excessive voltage drop can cause equipment to malfunction and reduce its lifespan. Therefore, it's important to select a cable size that minimizes voltage drop and ensures that the voltage at the service entrance remains within acceptable limits. Given these considerations, here are some recommended actions to take. 1. Verify load study assumptions. Review the load study methodology and assumptions with the consulting firm to ensure they accurately represent the building's load profile. Ask them to provide detailed explanations of their calculations, diversity factors, and assumptions about power factor and equipment usage. Challenge any assumptions that seem unrealistic or overly conservative. 2. Install metering on the existing transformers to monitor the actual demand load over a period of time. This will provide real-world data that can be used to validate or refute the load study findings. Use the metering data to identify peak demand periods, load patterns, and any unusual energy consumption trends. 3. Base the transformer sizing on the highest possible demand load that could be reasonably expected in the future. This approach provides a safety margin and ensures that the transformer has sufficient capacity to handle any potential load increases. Consider the impact of new equipment, expanded operations, and changes in building occupancy. Finally, consult with a qualified electrical engineer. An experienced engineer can provide guidance on the optimal transformer size and configuration based on all relevant factors. They can perform detailed calculations, assess potential risks, and ensure that the new transformer meets all applicable codes and standards. NEC Section 220. 87 allows using the actual recorded maximum demand to determine the load. The recorded demand, however, must meet specific requirements. It must be based on at least 1 year of metered data. The maximum demand must be adjusted to account for any known increases in load or changes in operating conditions. This method provides a more accurate representation of the actual load than estimations based on connected loads. Consider NEC Section 220. 6C1 for calculating the demand load for non-dwelling units. This section permits calculating the feeder or service neutral load as the maximum unbalanced load. It outlines specific requirements for calculating the neutral load based on the type of loads served. It accounts for the fact that not all phase currents return through the neutral conductor. NEC Table 310.16 provides ampacity ratings for various conductors based on their size, insulation type, and installation conditions. It is crucial to select conductors with adequate ampacity to handle the expected load current. Remember to apply appropriate correction factors for ambient temperature and the number of conductors in the raceway. NEC Article 250 covers grounding and bonding requirements. Grounding ensures that the electrical system has a low impedance path to ground. Bonding connects all non-current carrying metal parts to the grounding system. This minimizes the risk of electric shock and provides a path for fault current to flow back to the source, tripping the overcurrent protection device. NEC Section 450 covers transformers. This section addresses transformer installation requirements, overcurrent protection, and ventilation. It outlines specific requirements for transformer location, clearances, and fire protection. It also provides guidance on selecting appropriate overcurrent protection devices to protect the transformer from overload and short circuits. NEC Section 110. 3b requires all electrical equipment to be installed and used in accordance with the manufacturer's instructions. This includes transformers, switchgear, panel boards, and wiring devices. Following the manufacturer's instructions ensures that the equipment is installed correctly and operates safely. NEC Article 408 covers switchboards and panel boards. This article outlines requirements for panel board construction, overcurrent protection, and wiring. It specifies the maximum number of overcurrent devices that can be installed in a panel board and the requirements for bonding and grounding. NEC Section 230 covers services. This section outlines requirements for service conductors, service equipment, and overcurrent protection. It specifies the minimum size of service conductors, the location of the service disconnect, and the requirements for grounding and bonding the service. NEC Section 215 covers feeders. This section outlines requirements for feeder conductors and overcurrent protection. It specifies the minimum size of feeder conductors, the requirements for voltage drop, and a selection of overcurrent protection devices. Remember, voltage drop is a critical consideration in electrical system design. Excessive voltage drop can cause equipment to malfunction, reduce its lifespan, and waste energy. The NEC recommends limiting voltage drop to no more than 3% on feeders and 5% overall, including both feeders and branch circuits. Several factors contribute to voltage drop, including conductor size, conductor length, load current, and power factor. Larger conductors have lower resistance and therefore less voltage drop. Shorter conductor runs also result in less voltage drop. Higher load currents and lower power factors increase voltage drop. To minimize voltage drop, select appropriate conductor sizes, minimize conductor lengths, improve power factor, and balance loads across phases. Conductor ampacity is the maximum current that a conductor can carry continuously under specific conditions without exceeding its temperature rating. The NEC provides ampacity tables for various conductor types and sizes, taking into account factors such as insulation type, ambient temperature, and the number of conductors in a raceway. It's crucial to select conductors with adequate ampacity to handle the expected load current. The overcurrent protection devices protect electrical circuits from overloads and short circuits. These devices, such as circuit breakers and fuses, interrupt the flow of current when it exceeds a predetermined level. The NEC specifies the maximum allowable overcurrent protection for various conductor sizes and equipment types. It's important to select overcurrent protection devices that are properly sized to protect the circuit without nuisance tripping. Short circuit current is the high current that flows during a short circuit. This current can be many times higher than the normal operating current. Electrical equipment must be able to withstand the available short circuit current without being damaged. Short circuit current ratings are specified for various types of equipment, such as panel boards, switchgear, and transformers. It's important to ensure that the equipment's short circuit current rating is higher than the available short circuit current at its location. Ground fault protection is designed to detect and interrupt ground faults, which occur when current flows from a live conductor to ground. Ground faults can be dangerous, as they can cause electric shock and fires. Ground fault protection is typically required for services and feeders rated 1000 amps or more. It's important to test ground fault protection systems regularly to ensure that they are functioning properly. Harmonics are distortion of the voltage and current waveforms. They can be caused by nonlinear loads, such as electronic equipment and variable frequency drives. Harmonics can cause a variety of problems, including overheating of equipment, reduced power factor, and interference with communication systems. Harmonic filters can be used to mitigate the effects of harmonics. Power factor correction improves the efficiency of electrical systems by reducing the amount of reactive power. Reactive power does not contribute to actual power consumption but still flows through the electrical system, increasing the current and voltage drop. Power factor correction capacitors can be used to reduce the amount of reactive power, improving power factor and reducing energy losses. Surge protection protects electrical equipment from voltage surges, which can be caused by lightning, switching operations, and other disturbances. Voltage surges can damage sensitive electronic equipment. Surge protection devices divert the surge current to ground, protecting the equipment from damage. Electrical safety is of paramount importance. Always follow safe work practices when working with electricity. Energize circuits before working on them whenever possible. Use appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools. Lockout and tag-up procedures are used to ensure that circuits are de-energized before work is performed. Electrical codes and standards provide detailed requirements for the safe installation and operation of electrical systems. These codes and standards are constantly evolving to reflect new technologies and best practices. Staying up to date on the latest codes and standards is essential for ensuring electrical safety. In summary, load demand load calculations can stem from various factors related to the load study methodology, time of day, power factor, and load diversity. Consider future expansion, system redundancy, and voltage drop when planning the new transformer. Verify load study assumptions, monitor actual load, and consider worst-case scenarios. Consulting with a qualified electrical engineer ensures optimal transformer sizing and configuration, adhering to all relevant codes and standards.